Hi everyone. In this session, we are going to see about multi-layer perceptrons or non-linearly separable data in neural networks, exploring techniques for non-linear data classification. Abstract of this experiment, multi-layer perceptron MLP on non-linearly separable data. Objective, program implementation, execution and results, applications. First, let's see about what is meant by multilayer perceptron. Here is a multilayer perceptron MLP overview. In this given diagram, we have input layer, hidden layer, output layer with two biases. What is a multilayer perceptron? MLP is a fully connected neural network with an input layer, one or more hidden layers, and an output layer. It uses backpropagation for training and activation function to introduce nonlinearity. Presence of hidden layer allows MLP to learn from non-linearly separable data. So these hidden layers are really helpful to learn from non-linearly separable data. So it uses backpropagation for training and then activation functions such as ReLU or sigmoid functions to introduce non-linearity in the MLP. So MLP is a fully connected neural network which has one input layer, one or more hidden layer and an output layer. Why MLP for non-linearly separable data? Linearly separable data can be classified with simple models like logistic regression or support vector machines. For non-linearly separable data such as XOR problem, circular patterns, these models fail as they can't draw curved decision boundaries. MLP solves this by introducing hidden layers that help capture complex relationships and nonlinear patterns in the data. So here linearly separable data can be easily classified, and for non-linearly separable data, this simple models like logistic regression or support vector machine, as they fail, they can't draw curved decision boundaries. This is why the need of MLP to solve this by introducing hidden layers that help capture complex relationships and nonlinear patterns in the data. So, objective of the experiment. The objective is to use MLP to solve XOR problem, which cannot be solved using linear classifier. This demonstrates how a neural network with a hidden layer and nonlinear activation functions can learn to classify non-linearly separable data. Program implementation. When it comes to program implementation, the first and foremost thing is about algorithm. So here is an algorithm for our program. Step 1. Initialize the input patterns for XOR gate. Step 2. Initialize the desired output of the XOR gate. Step 3. Initialize the weights for the two-layer MLP with two hidden neuron and one output neuron. Step 4. Repeat the iteration until the losses become constant and minimum. We have to compute the output using forward pass output and compute the error and compute the change in weight DW by using backward propagation algorithm. Modify the weight as per delta rule. Append the losses in a list. Step 5. Test for the XOR patterns. This Python program implements a simple neural network with a single hidden layer to solve the XOR problem, which is a classic example of non-linearly separable problem. Here's a breakdown of the code and its functionality. Data initialization. The input X represents the XOR input with 4 combinations of binary values. The output Y corresponds to the XOR truth table, where the XOR operation outputs 1 when the input differs. Neural network structure in 2 input neurons for XOR input and 2 hidden neurons in the hidden layer and 1 output neuron to predict the XOR result. Third, weight initialization. Weights are randomly initialized using np.random.rand, where weights between input and hidden layers. Activation function. The sigmoid function is used as activation function to introduce nonlinearity into the network, which is defined as def sigmoid function. Forward propagation. The forward pass computes the activation at each layer using the current weights. Backward propagation. Backward propagation calculates the gradients of the loss function with respect to the weights and updates them accordingly. Training loop. The weights are updated using the backpropagation results for 10,000 iterations. The loss is recorded and plotted. Prediction. The predict function evaluates the network output for new input values. Now let's dive into the execution and result. The program successfully trains the MLP model first to classify XOR data. After training, the loss decreases over time, which indicates that the model is learning to minimize error. This would be the result, which has input, output, and epoch. Now let's see about the applications. First, solving nonlinear classification problems. MLP is effective for nonlinearly separable problems such as XOR and other complex data distributions. Handwritten digit recognition. MLPs are used in recognizing digits, example MNIST dataset, due to their ability to learn from image data. Third, medical diagnosis, used for classifying patient data and detecting patterns in medical images for disease diagnosis. Fourth, speech and image recognition. MLPs play a key role in early-stage neural network model for recognizing speech and images. Now let's end our session with the conclusion. Thus, this experiment demonstrates a simple implementation of MLP solving the XOR problem, illustrating how neural networks can learn nonlinear pattern efficiently. Thank you all.